Hello, everybody. Welcome to today's lecture. So we already talked about whole numbers, addition, and subtraction. Okay, so make sure you watch those videos if you haven't already, especially addition, because we're going to kind of build off of it here while we talk about multiplication. Okay, so today we're going to finish up chapter 1 and talk about multiplication and division. Okay, which are pretty similar to each other, right? They're inverses of each other, just like addition and subtraction are inverses of each other. So first, let's get to what exactly is multiplication? So what if we say we want to do 5 multiplied by 3? What do we mean by that? Well, multiplication, it's really just a fancy way of saying do addition over and over again. Okay. So if we say we want to do 5 multiplied by 3, what we really want to do is we want to add 5 to itself 3 times. Okay, so we want 3 copies of 5 added together. So the first number tells you, okay, what number are we working with? The second number tells you how many times are we adding it. Okay. So of course here we get 15. So this is really just repeated addition. Okay. So if you look at it at the context of say we have this it looks like a square, but let's say it's a rectangle, right? And we have the length on this side is 5 and the length on this side is 4. And what we mean by that is that if we had like draw this a little better here. If we had boxes on this side, if we drew it like this, so it's not exactly to scale, but if these all have 1 unit of length on each side, so let's say it's like 1 inch or something on each side here, then we have 1 plus 1 plus 1 plus 1 plus 1 is 5 inches altogether. And then on this side, we have 1 plus 1 plus 1 plus 1 for 4 inches altogether over here. Okay. So if we want to do 5 multiplied by 4, there's a couple of different ways we can write that. One of the more common ways we usually start to write it is by writing 5 cross 4, or like 5x4. It's really like a cross. But we want to avoid this way because later we're going to be using x as a variable a lot, and it's easy to get them confused. But I'll introduce the other notations in a second. First, let's just think about what does 5 times 4 mean? Well, visually with this picture right here, what we're really asking is how many boxes are there total? Okay. If there's 5 boxes going down this way and there's 4 boxes on this side, how many boxes are there altogether? So we could just go through and count them. 1, 2, 3, 4, 5. This would make 10, 15, and 20. Okay. So the answer to this should be 20. If we do it with the repeated addition, then we have 5 plus 5 plus 5 plus 5. And you can see this is basically just adding up all the columns, right? There's 5 boxes here, 5 boxes here, 5 boxes here, 5 boxes here. Add them all together to get 20. Whoops. Sorry, my display is not working properly. So I can't really see what I'm writing, but there we go. That looks right. So we have 5 plus 5 plus 5 to get 20. Now, notice that it doesn't really matter which order we do this in. If we want to know instead what's 4 times 5, well, that's just like looking at it from the other angle. So we should get the same thing. Let's make sure though. We're going to do 4 plus 4 plus 4 plus 4 plus 4, because now we're adding up this row plus this row plus this row plus this row plus this row. So this one's like adding the rows up. This one's like adding the columns up. At the end of the day, we're going to get the same thing. Okay. So with multiplication, just like addition, the order doesn't actually matter. You can do 5 times 4 or 4 times 5, and you're getting the same thing. Okay. So it's just shorthand for repeated addition. So some notations for multiplication here. Like I said, there's 5x4. That's one way to write 5 multiplied by 4. A more common way would be with a dot. So 5 times 4 would be like 5.4. Another more common way, whoops. Sorry, my display is messing up here. I think my computer's just getting too hot. Whoops, not 20. We want to have 4. Okay. So we have 5 parentheses 4. Or we could put the 5 in parentheses also. Okay. If we have a variable, which we haven't talked about, but like a letter, which represents a number, we just don't know what the number is, then maybe we would write, and if we want to do 5 times y, for example, where y is our variable, we would just write 5y with them right next to each other. So this is just like with the parentheses way. The reason we put the parentheses when we have two numbers, though, is because we want to know that it's 5 times 4 and not 54, right? With the 5y, we don't really have that confusion because we know y isn't a digit, it's an actual number. So we don't need the parentheses there. So all of these are different ways to write multiplication. Okay. So the repeated addition method works fine, but what happens when we want to do bigger numbers? Because just like when we did addition, when we had small numbers, it was fine to just count them up, see what we get. But here, but with the addition, once we got the bigger numbers, it was tougher to count them. Same thing here. Once the numbers are bigger, it's going to be harder to do that addition. Like if we have 5 times 125, well, do we really want to add 5 to itself 125 times? Not really. We could do it the other way. We could do 125 added to itself 5 times, but that still is going to take a long time. So what's a better way to do it? Just like with addition and subtraction, we have this nice algorithm where we can line up the place values and do it that way. So first I'll show you how the algorithm works, and then I'll kind of explain what's going on, what's really going on with it, okay? So we set it up the same way that we do addition and subtraction. We line up the place values, with the exception of if it ends with a 0, then we don't have to, but I'll talk about that later. And then what we do is first we multiply the ones place. Okay, so when we do that, 5 times 5, we get 25. Now, just like with the other ones, we take the ones place number, the 5, and put it with the ones, and then we carry the other number. Okay, so we carry the 2. But now it's a little bit different what we do. Okay, so now we multiply. Notice we don't have any number in the tens place for the second number, the 5. Okay, so we're not actually multiplying the tens place together. Now what we're doing is we're taking the bottom 5 here and we're multiplying it by the tens place of the first number. And that'll make more sense once I break down what's going on here. So we're doing 5 times 2. Okay, 5 times 2. And then after we do that, we're going to add the other part of it. We're going to add that 2 in. So we're not going to multiply it, actually. We're going to add. Okay. So 5 times 2 is 10. 5 plus 5 plus 2 is 12. Okay. And then same thing. We're going to leave that last digit here and then carry the next one over. And then we do something similar. We're going to take the 5, multiply it by this 1, and then add whatever's left, which is the 1 here. So we're doing 5 times 1 plus 1. So 5 times 1 is 5. Anything times 1 is going to stay the same because that's just saying we just have one copy of it. Okay. And then we're going to add 1 to get 6. And then we're done. 125 times 5 is 625. Okay. So this one's a lot more strange than the addition and subtraction algorithms. So let's talk about what's really going on here. When we're doing 125 times 5, we're using what's called the distributive property, which we'll take a closer look at later on. But essentially what that means is, remember 125, we can break that into the hundreds, tens, and ones place. So we get 100 plus 20 plus 5. Okay. So 125 and the 100 plus 20 plus 5, same thing, right? We're just breaking it up into its places. And now we're using the fact that, okay, what we can do is we can take this 5, multiply it by the 100, multiply it by the 20, multiply it by the 5. Okay. That's what's called the distributive property, is that when you have addition and multiplication mixed like this, you can, like the way this is written, it's saying do the addition first, then multiply. What the distributive property says is we don't have to. We can actually do the multiplication first, then add it together. So we can do 100 times 5 plus 20 times 5 plus 5 times 5. Okay. So that's what's really going on behind the curtains of this algorithm up here. So 100 times 5 plus 20 times 5 plus 5 times 5. And that's all we did when we were doing the algorithm. First, we did 5 times 5 to get 25. Then we did 5 times this 2 is really like 5 times 20. We just don't have to worry about that 0 because what we're doing is we're putting it in the tens place anyway. So the extra number we don't have to worry about. And then when we're doing the 5 times the 100, the extra 2 digits we would get 500, right? Those extra 2 zeros don't matter because it's going in the hundreds place anyway. So that takes care of that. So what's weird still is that we have to add these numbers up here, right? So when we do 5 times 2, we got 10, right? And then we added 2 to get 12. And then we did 5 times 1 to get 5. And then we added 1 to get the 6. So let's think about, like, okay, if we just had it broken down like this, now what would we do? Well, 100 times 5 is 500. 20 times 5 is 100. 5 times 5 is 25. So these ones we could all just do by repeated addition, right? We could do 100 plus 100 5 times, 20 plus 20 plus 20 plus 20 plus 20 5 times. And then this one we already did earlier. So now we have an addition problem. So what do we do with this? Well, if we wrote it out like our last addition problems, and this is what happens. We get 5 this way, 2 this way, and then 6 right here. So that's where these numbers up here are coming into play, where we're adding them in. It's to account for this 2 right here and this 1 right here. Okay. So I know this is kind of weird, and I'm not expecting you guys to like know how to do it this way, how to break it down like this. I just want to break it down so that you understand where this is coming from. It's not just coming out of nowhere. We typically teach this as just like some steps to memorize, but this is what's really going on behind the curtains. If this doesn't make sense right now, that's fine. What I'm hoping is that like more towards the end of the semester, after we've had a lot of practice and we've talked about algebra properties, like the distributive property, this will make a little bit more sense then. Okay, I just want to explain the mechanisms a little bit so it doesn't seem like it's coming out of nowhere. Okay. All right, so with that being said, what happens, here we have a 3-digit times a 1-digit. What if we have more than 1 digit here? Because then it kind of changes a lot. What if we have 125 times 12, for example? Well, if we think about breaking it down again, this is like 100 plus 20 plus 5 times 10 plus 2. So what we want to do is we want to take the 10 and multiply it by all of these, and the 2 and multiply it by all of these. At the end of the day, we want to make sure that every place, the hundreds place, the tens place, and the ones place in this one is multiplied by every place in this one, the tens and the ones place, which is another thing we'll talk about this more in detail later, but that's what's going on behind the curtains of the algorithm here. So the way we started is exactly the same as we did the last one. We take the ones place of the bottom number and multiply it by all the place values in the top number. So 2 times 5 is 10. We put the 0 here and carry the 1. 2 times 2 is 4. Add the 1 to get 5. Okay. And it's just 5, so we don't have to carry anything. And then 2 times 1 is 2. Okay. So we did 2 times 125 to get 250. Now we have to take care of this 1. Now, what's important to note is that 1 is in the tens place. So we're not really multiplying by 1, we're multiplying by 10, but we don't want to multiply by 10 every time. So what we're going to do is on the second line here, we're going to put this 0, and that is going to help us account for the fact that this is really a 10 instead of a 1. Okay. So the difference between multiplying by 1 and multiplying by 10 is literally just a 0 at the end of the number. For example, if we do 9 times 10, we get 90. If we do 9 times 1, we get 9, right? So that 0 at the end is all that's changing. So what we can do is we can put this 0 here, and then all we have to worry about is multiplying by 1 instead of multiplying by 10 every time. And we're adding a new line here because what we're going to do is we're going to multiply by this number and then add the 2 together. So looking back at how we broke it down, the first line here is multiplying everything by 2. The second line here is going to multiply everything by 10, and then we're going to add them together at the end. So now we're going to take this 1 and multiply it by every number. And we can forget about this 1 up here. We already used it. So 1 times 5 is 5. Hang on, let me wait for my display to load. There we go. 1 times 2 is 2. And 1 times 1 is 1. Okay. So the first line is the 2 times everything. The second line is the 10 times everything. Now we just need to add them together. So we kind of have an addition problem within the multiplication problem. So we have 0 plus 0 to get 0. 5 plus 5 is 10, so we have 0, carry the 1. 2 plus 2 is 4, plus 1 is 5. And then 1 plus nothing is 1. So we end up with 1,500 at the end for our answer. Okay. You can always use a calculator to check to make sure you're doing these right. On the tests, I'll be asking you to show your work on these problems, but feel free to use a calculator to check them since it's all going to be online anyway. obviously you can't be stopped from using a calculator, so feel free to use that to check your answer. You'll just need to show your work to show that you know how to get to it by hand. Okay. All right, so this is really just something that comes with practice because, like I said, like these are really just steps to memorize. Knowing what's going on behind it helps you remember the steps, but to actually execute the problems, you have to remember the steps. Let's do a couple more examples with that in mind. Let's say 754 times 891. It's a pretty big one. But the steps follow the same way. So we have 1 times 4 is 4. 1 times 5 is 5. 1 times 7 is 7. Okay. So we multiplied the ones place by everything on the top. Now we want to take the tens place and multiply it by everything, but because we're in the tens place, we should add a 0. Okay. Oops. So we have our 0 here. Draw it better. Now, we can just go ahead and do the multiplication. So 9 times 4 is 36. So we have 6, and then we carry the 3 over. 9 times 5 is 45. And then we're adding 3 to it, so we get 48. So we have 8, and then 4. 9 times 7 is 63. And then we're adding 4 to it, so we get 67. There's nowhere to carry it, so we just bring all of it over. Okay. Now, if these aren't, I have these memorized, so I'm doing it kind of quickly, the 9 times 7 and 9 times 5. So feel free to like pause the video if you want to, work out what the 9 times 5 is and the 9 times 7 is, right? So you just want to do the repeated addition when the numbers are this small. So you just add 9 to itself 5 times, add 7 to itself 9 times, that kind of thing. Okay. So the idea with these large number of digits in the multiplication problems is we're breaking them down into single digit multiplication so that it's easier to do the repeated addition methods. So now, all right, we don't need the 4 and the 3 because we already used them in the last step. Now we're multiplying 8 by everything. 8 is in the hundreds place. So instead of just 1 0, we're going to need 2 zeros. So every time we move over a place, we add an extra 0. So in the first step, we add that 1 0 right here. In the second step, we'd have the 2 zeros. If we had a thousands place, we'd have 3 zeros when we get to that step, and so on. So 8 times 4 is 32. Okay, and then we're going to carry the 3. 8 times 5 is 40, plus 3 is 43. Okay, and then we're carrying the 4. So here it happened to be the same numbers, but that's just a coincidence. 8 times 7 is 56, plus 4 is 60. Okay. So we end up with this, and now we need to do an addition problem. Sorry, that should be addition. So we have 4 plus 0 plus 0 is 4. 5 plus 6 plus 0 is 11, so we carry the 1. Let me write that better. Sorry, my display is messing up, so I just have to wait a second for it to load. 8 plus 7, 7 plus 1 is 8, plus another 8 is 16, plus 2 is 18. Okay. 7 plus 1 is 8, plus 3 is 11. You can also carry the comma down. 1 plus 6 is 7, and then we just have 6 here to get 6. So we have 671,814. Now, there was a lot of places where that could have went wrong, so let's throw it in the calculator just to make sure that we did it correctly. And I get the same thing, 671,814. So we can confirm we did it correctly. Okay. So this is the exact process we'll use for all of these problems. So just, do some examples on your own, and make sure you have it down. The only thing we didn't talk about is what happens when you multiply by 0, right? Okay, so what's like 9 times 0? Well, 9 times 1 is 9, because it's just saying, okay, we have this many copies of 9, right? And 9 times 2, well, this is saying we have 2 copies of 9 we want to add to each other, so we get 18, etc. 9 times 0 is saying we have 0 copies of 9, right? So we just don't have anything. We have 0. Maybe an easier way to think about it, 0 times 3, for example, or rather, I'll just use a smaller number here, 3 times 0. We know multiplication can be done in any order, so this is the same thing as 0 times 3. So this is saying add 0 to itself 3 times, which of course is just going to be 0, because we're not actually adding anything. So anything times 0 ends up being 0, okay, including itself. 0 times 0, you get 0. Okay. One little trick we can use if something ends in a 0, if we want to do 88 times 90, for example, well, the 0 at the end, like I said before, the only difference between multiplying by 9 and multiplying by 90 is that there's a 0 at the end. I think I used it with 10 and 1, but it's the same idea here. So what we can do instead is sometimes we'll write it like this, with the 0 kind of off to the side here. And then we just carry the 0 down with us, because what this is saying to do is it's saying, okay, just multiply by 9, and then whatever you get, just put a 0 at the end of it, and then it's the same thing as multiplying by 90. Okay. So 8 times 9 is 72. 8 times 9 is 72, so we get 79. So 88 times 9 is 792, which implies 88 times 90 is 7,920. Okay, so the only difference is putting a 0 at the end. So this is just a little trick you can use when things end in 0 to make it faster. You can just do it the long way with the 88 times 90, right? You do 0 times 8 is 0. Whoops. 0 times 8 is 0. Now in the next step, we need a 0 here because 9's in the tens place. 9 times 8 is 72. And then we have 72. And then we just add them, but the first one is 0, so you just get the 7, 9, 20. Okay. All right, so that is all for a addition. So it's been about a half hour, so we're making good time. Whoops, I made a typo here. So now let's talk about division. Okay. So like I said, addition and subtraction are inverses of each other. And in the same way, multiplication and division are inverses of each other. So when you add something, subtraction takes away like whatever you added. It's the exact opposite thing. In the same way, if we want to divide something, like for example, 15 divided by 3, one way we can think of this is, okay, 3 times what would give me 15? Okay. That's kind of like an algebraic way to think about it. Maybe a easier way to think about it is, okay, say we have 15 of something and we want to split it into 3 equal groups. How many things would be in each of the groups? So we have 15 of something and we want to split it into 3 groups here, right? So let's say we have $15, and then let's say we have 3 kids, right? Kid 1, kid 2, kid 3. You can give them names if you're more creative. And you want to give them all an equal amount of money. How much do we give them each? right? So in this case, we would just come up with 5. How we come up by 5 is a little tricky. We really just have to think of it like a multiplication problem. We just have to think like 3 times what is going to give us 15. Knowing our multiplication tables really helps here because with the small digits here, there's really not a way to break it down. When we have larger digits, we'll have what's called long division. But even that is really just turning it into a multiplication problem. The way we do division is just by turning it into a multiplication problem. So first, some notation. Okay. 15 divided by 3. This is probably one of the common ways to write it, right? A minus sign with dots on the top and bottom. Oh, one thing I forgot to mention about multiplication is that our answer here, the 15 or whatever the answer is, it's called the product. Okay. So we say 15 is the product of 5 and 3. So with subtraction, our answer was called the difference. With addition, it was called the sum. Multiplication, it's called the product. With division, the answer, which in this case was 5, the answer is called the quotient. Okay, quotient. And the other parts of it have names too. The 3 is called the divisor, but we don't really use those names quite as often, at least not in this context. We'll look at that a little bit later in chapter 2 when we're talking about like factors and stuff like that and divisors. All right, so we have the 15 divided by 3. 15/3 is also pretty common. This is kind of usually used for typing in place of writing this. 15/3 is sometimes how we'd read this, or like as a fraction, 15/3, or just 15 divided by 3. But it's 15 on top, 3 on bottom, and a bar in the middle. We use the / to kind of type it this way when it's hard to, if there's not like a program that'll let you write it as a fraction. Okay. I think these are pretty much the only ways. I don't think I'm forgetting any. One way I never actually mentioned with multiplication, now that I'm thinking about it again, let me just add this in here. 5*3. Not a very good asterisk. And also, this is another way that's really only used with typing. But this is an online class, so if we're gonna be typing, this is maybe usually we use 5*3 because it's not really possible to write 5.3. Okay. So let's look at some examples, right? Like what about 20 divided by 4? Well, we want to know 4 times what is equal to 20 is really what we're asking ourselves. So we just have to go back to the multiplication tables to come up with 5. A lot of it is just really trial and error with finding the right number to multiply by. What about 10 divided by 5, right? We're saying 5 times what is equal to 10. And then we would just try a couple things and we come up with 2. Okay. Now, what about 17 divided by 1? Well, we're saying what times 1 equals 17. So this is, of course, just going to be 17 because anything multiplied by 1 stays the same. So, by that logic, any number divided by 1 will also stay the same, right? So any number, say like y divided by 1, is just going to stay the same. It's going to be y. Okay. What if we do 0 divided by 5? What times 5 equals 0? Well, 0 times anything equals 0, so the answer has to be 0. In fact, no matter what the number on the bottom is, the answer is 0, assuming y is not equal to 0. Because 0 divided by 0 is not necessarily 0. That's what we call indeterminate. Okay. I'll explain that in a second. First, let's think about why the dividing by 0 is makes things complicated. Well, if we're doing 10 divided by 0, we're asking ourselves 0 times what equals 10? But we know that 0 times anything has to be 0, so there's no answer here, right? There's nothing this could possibly be, because anything times 0 is just going to be 0. It's not going to be 10. Okay, so this is undefined. Okay. So dividing by 0 is something that's just not possible, because it doesn't make any sense once we flip it around to multiplication, which is what this really is. If we want to think about it like more in like a real world context, if we have 10 of something and we want to split it between 0 people, how much do we give all of them? Well, that's not really a question that makes sense, right? We can't give 0 people anything. If we're saying okay, we have 10 of something and we want to give, like, say we have $10 and we want to give $0 to everybody, how many people can we give $0 to? Well, then the answer is, you could just keep doing that forever, because when you give 0 of it, you're not really taking any of it away, right? You still have $10 even if you give 0 of it away. So there's no end there, right? So either way we think about it, it's not a question that makes sense. So we just say it's undefined. One exception to this coming from this part is, if we have 0 divided by 0, the question's a little bit different, because if we're saying 0 times 0 times what equals 0? Well, 0 times anything equals 0, right? So this isn't necessarily undefined. It's just that we can't possibly know what it is, because it could be literally anything. So it's what we call indeterminate. Okay, so right now we don't really need to worry about the difference between 0 over 0 and 10 over 0. We never will in this class. For our purposes, if 0 is on the bottom, if we're dividing by 0 in any capacity, it's not something that has an answer, right? It's just undefined or whatever. You don't have to distinguish between undefined and indeterminate. But the differences do come into play later. Indeterminate usually means it's not determinate in this form. Maybe we can do something else to it to determine what the answer is. Whereas with undefined, that's it, right? We can't do anything with that. So let's go ahead and so we've only looked at not single digits necessarily, but small numbers, right? So what happens if something's just like too big? What if we have 125 divided by 5? Well, we could sit here and think, okay, 5 times what equals 125, but there's a lot of options here. the answer ends up being 25. So if we wanted to really guess, we'd have to guess, 1, 2, 3, 4, 5, 6, 7, all the way up to 25 and do the multiplication every time until we figured out that that was the answer. A better way to do this is by what's called long division. Okay. So long division. So long division kind of breaks down the problem a little bit so we don't have to guess so much. The way we write it is like this. We put the top number on the inside of this like half rectangle and the bottom number on the outside. So let's actually add this to our notation list, right? 15 divided by 3. So we kind of write it backwards from how we read it. So what we do is we say first, okay, let's take the first digit and try to divide that by 5. So we say, let's do 1 divided by 5. Well, 1's not big enough to divide by 5, so that one doesn't work. So now let's include the next digit and see if that's big enough. Okay. So if 1 was big enough, we would just do the division. If not, we move on to the next digit. So now we say, okay, what's 12 divided by 5? Or what's as close as we can get to it? The way we usually word it is, how many times does 5 go into 12? And the answer is 2 times, right? Because we can get close to 12 with 10. So 5 goes into 12 2 times, but how much is left over, right? And the way we determine that is we say, okay, 5 times 2 is 10. So if we subtract that from the 12, we have 2 left over. So in other words, 12 divided by 5 is 2, but then we have 2 left over, or 2 with a remainder of 2. So to recap, we say 5 goes into 12 how many times? 2 times. Now 5 times 2 is 10. 12 minus 10 is 2, so we still have 2 left over. So now with that 2 left over, we bring down the next digit, which is 5 in this case, and then we start over. We say 5 goes into 25 how many times? And in this case, it'd be 5. Now 5 times 5 is 25, so we don't have anything left over. So then once we run out of digits to bring down, we're done. Okay, so our answer is 25. So it's just like with the addition and subtraction multiplication algorithms where we break it down into smaller numbers that we can work out by hand or in our head. Okay. So let's say we have 246 divided by 2. Okay. So we say 2 goes into 2 how many times? Well, just 1 time, right? Because it's the same number. 2 times 1 is 2. Now 1 times 2 is 2. So we subtract that off and we get 0. And then we bring down the next digit and we keep going. So we say 2 goes into 4 how many times? 2 times, right? Because 2 times 2 is 4. And then because 2 times 2 is 4, we don't have anything left over. So we don't really have anything left over in most of these ones. And then we bring down the 6. And we say 2 goes into 6 how many times? We get 3. 3 times 2 is 6, so we don't have anything left over. So our final answer is what's up here, 123. Okay. Now I said we stop once we run out of digits. What happens if we don't end up with 0 at the bottom? Let's say we have 625 divided by 3. Okay. So 3 goes into 6 how many times? 2. And then 2 times 3 is 6, so we don't have anything left over. Now we bring down the 2, and we say 3 goes into 2 how many times? Well, 2 is smaller than 3, so 0 times. Okay. 0 times 3 is 0, so we still have 2 left over. Okay, we have all of it left over this time. Now we bring down the 5. 3 goes into 25 how many times? Well, 3 times 8 is 24, so we get 8. Okay, so we're just seeing like what can we multiply it by until we get as close as possible without going over. 3 times 4 is 24. So we have 1 left over still, but we're out of digits to bring down, right? There's nothing left here. So our final answer is 208, but we still have the 1 left over. So the way we say our answer is we have 208 with a remainder of 1. Okay, so we write R1. This is saying we have 208, but we have 1 left over. Okay. So we'll have different ways to write this later, like 208 and 1/3, for example, or we'll write it as a decimal, but we'll talk about those in the fraction and decimal chapters. For now, we're just going to write it as 208 remainder 1. If you put this in your calculator, you'll probably get 208.33333 forever, and that's what we would get if we did it with a decimal, but that's the same thing as just remainder 1. Later we won't want to use the remainder notation because it's a little bit ambiguous, because the remainder of 1 is based on this 3 here. If this was a 4, the remainder 1 would mean something completely different. So this is a little bit ambiguous. It depends on what we're dividing by. So we'd rather replace that with like a fraction or something, but we'll get to that in chapter 4. For now, we're just going to write remainder 1. Okay. So let me just make sure I haven't missed anything. Don't think I have. No. So the main thing for this chapter is practice, right? I know I say that a lot, but it's really true. I can only show you so many problems before you really just need to try them on your own. I'm going to go through one more here and really break it down. But after that, I just encourage you to do some problems on your own, and you will have homework problems with this where you can practice it. So let's do a smaller one so I can write out in words everything that we should do. Okay, I'll go down a little bit. Let's say we have 78 divided by 4. Okay. So first we say 4 goes into 7 how many times? Okay. So this is the first thing we ask ourselves. 4 goes into 7 how many times? The answer is 1, right? So 2, we do 4 times 1. And write the answer beneath the 7. Okay, because we're setting it up for subtraction. So 4 times 1 is 4. And 3, we want to do 7 minus 4, 3. So this is just a long way of saying 4 goes into 7 1 times with a remainder of 3. In other words, if we did 7 divided by 4, we get 1 with a remainder of 3. Now, bring down the next digit. And then we just want to repeat until we run out of digits. Okay. So 4 goes into 38 9 times. 9 times 4 is 36. So we get 2. So this is our answer. It's 19 with a remainder of 2. Okay. If we had more digits, we would just keep going until we run out of the digits. Okay. All right. So this is the end of chapter 1. So this is the end of the arithmetic section. So like I said, you really just have to practice this stuff to kind of just remember the steps for all of these, because all of these are just remembering the steps for how to do the problems. It really helps if you know why we're doing the steps. It helps you remember them better. So make sure to go back over that stuff. Let me know if you have any questions. I'd be happy to go into more detail or just go slower or whatever you need to understand it. I encourage you to use your calculator to make sure you get the right answer. Luckily, with these arithmetic problems, they're really easy to check because the calculator can do any one of them. Okay. And then I think that's it. So, there will be more of these in the homework to practice with. And yeah, next time we'll move on to chapter 2, which is the beginning of algebra. So we'll just have a lot of definitions. So it'll be a little bit of a change of pace. So yeah, thanks for watching this video, and I will see you next time.